Start the idea. Okay, so thank you all for coming back. I apologize for the last week. I was unspoken. Today I would like to come back a little bit just to do some basic goals about the project space we already did last session. So the main object we were interested was P and N, so the projective end space. Now, we obtained it. Okay, so I'm just going to do some notation, but I'll mainly try to draw some stuff about it. So we just introduced it as a equivalence relation on n plus 1 affine space with the origin rule. So we'll have a point of n plus 1 coordinates, and we associate it with its homogeneous coordinates. Okay, so in order to understand this, well, it's kind of like, well, we did something very closely to what differential geometries do, meaning that we'll try to cover x by affine chunks. Sorry. So inside of this, for any choice of a coordinate, we can find a copy of the end space inside of it. So how do we do it? Well, consider, for instance, that we chose the very easy one. We just chose the points where x0 is not equal to 0. It's not equal to 0. So imagine that your an plus 1 space is, this is not good. Imagine that the end space is something that resembles this, and you choose one of the coordinates to be non-zero. This will be, you'll find here, so the project, so imagine that this whole free space here is the n plus 1, and we want to find P2. So what I'm trying to draw here will be the project, P2. Okay. So what is the projective space? Well, we consider every line, and we consider every line as a point of the projective space. So every line which won't be horizontal, you have this horizontal, but if it is not containing this plane which is parallel to this plane here, so let's say this is x, this is y, this is y. So these are not standard coordinates, but let's just assume that that's this. So every line which is not parallel to this plane will intersect this plane in only one point. Okay? So these points of the parallel line will be A from B. So this is so this will be a chart. Well, a very easier way to represent it, let's say projective line. You have here x equals 1, and every line which is not parallel to this vertical line will intersect this section here in only one point. And this you can choose another one and another one and another one. So every point will be inside of one of these types of affine pieces inside of the projective space. And the other points, which are not, which don't intersect this chart, will be called the points at infinity. So every line which is parallel to this, which is inside of this plane here, will be called the points at infinity. And as it turns out, you can just, these points will also form something is isomorphic to a projective space, which will be well, this will just be P1. Yeah. Like that. So you can consider that P2 is just A2 with 0.750. Okay. So this is kind of how you do it in differential geometry as well. You choose one of the coordinates. It's an affine plane, so everything is more or less okay. But, okay, so how do we do algebraic geometry inside of it? We want to find things which are inside of Pn, which look like solutions to polynomial equations. Well, for that, we needed the idea of a projective cone, right? So, well, no, a fine, sorry, it's the other way. So, if we had P of n somewhere here, we'd like to understand projective, let's say, set, an algebraic set inside of it. So I just drew something like an affine chart for Pn. It's just that. But it is embedded inside of 1 plus 1 dimensional space. So let's consider Pn as the as something that comes from an plus 1. So this is the origin. And we can consider all the lines that go through the origin, something like this. And this forms what is called a cone. Okay, so this is x, and this whole thing here, or if I call this the something like projective pi, right? So this will be the affine cone associated to it, like that. And this will be an algebra, and we want this to be an algebraic set. So this is how we kind of do, every question we wanted to ask about the projective space, we kind of bring it back here. We already know how to define algebraic sets and all this kind of stuff about topology. We do it here, and we drag it back down. So this is kind of the image we have. So this is how we intuitively wanted to ask to define the homogeneous ideals, and this is also how we talked about the projectivization, and this is how we were brought to the projective Newtons. So just the same way, homogeneous ideas correspond to projective sets, subsets inside of Pn. Well, the radical for the homogeneous ideas correspond to projective sets. Okay. So everything inside of here, X will be something like this, where S can be. So this is the zero locus of a set of polynomials. This can be either a homogeneous ideal or a set of homogeneous polynomials. Like that. Okay. And if we consider I of x, this will be the ideal, let's say, of this projective variety. Okay, so for something projective, this will only be the affine ideal of this algebraic set here. Okay, so this is kind of how we built again the correspondence between ideals and varieties. Okay, but now one of the things I wanted to talk about today was the link between the topologies here and the topologies here. So what happens to the level of these affine charts? Okay, So what I want to say today will be about how actually these topologies are consistent between the two, and how I can take a closed subset here and take its closure inside of here. This will be called the projective closure, and it will be linked to the homogenization and dehomogenization of polynomials. And lastly, I will also talk about morphisms and regular functions, so the whole treatment we already did here. And hopefully we'll start about talking about smooth points soon enough. Okay, so let's talk about topology for now. The rest of topology will be made of, well, as you can imagine, these sets here. Okay? So the VP of S form the closed sets of a topology called, well, let's say topology. So what we need to say that, well, some basic formal arguments, like we want them to be closed under finite unions. So if I take the union of just two of them, what do they contain? I just take the product. It's also the product. And this will give me the union. Okay. So remember that if these are just sets of homogeneous polynomials, their products will also be homogeneous. So there's no real problem. Let's see. And and if I take arbitrary intersections, well, this is just the reverse operation. I just take unions here, and that basically works quite fine. Okay. So this will give me a topology, and as one could imagine, there's the whole thing we already mentioned about how the topology gives us irreducible sets. So just like in the affine case, we can define, let's see, we'll have enough room here. Reducible subsets. So it is not the union of two proper closed subsets. Okay. This, let's see. Yeah, maybe I'll have to. Okay. So, like we did for affine case, we can define dimension. Alright, so the dimension will be maximum length. Of chains of reducible closed subsets of S. Okay. But actually we can give even a more precise statement. We can actually prove that the dimension of X, well, we can relate it back to the dimension of it's called to be the dimension of C of x minus 1. Now the minus 1 comes because we contract one dimension by taking this, by taking the projective image. Right? Lines become a point, so it's normal that we should deplete one dimension. Like that. Okay. So, what's a projective variety? Well, a projective variety is just an irreducible projective set. Well, subset of P of some P or some. And okay, and we will probably also call a quasi-projective variety. Quasi. Will be an open subset of some projective variety. Okay, so these are most basic ones. So this is the most general object we'll work with. When we'll talk about the variety, we will either mean an affine, a quasi-affine, projective, or quasi-projective variety. So, and usually they are always very similar to one. Okay, so let's see. Okay, so I'll start by erasing some of these diagrams. Okay. Yeah, so now we're going. Okay, so now what I am interested in is the relationship between the two topologies here, right? So we know that we have a Zariski topology here. We just talked about the Zariski topology right here. And we want to know a little bit about how to relate the two. So I'll just suppose here that this embedding comes from the fact where x0 is not equal to is not 0. Okay. So a point with coordinates x1, xn will be sent just here to this point here. And any point in that has x0 non-zero, then we can just divide by x0 inside of the homogeneous coordinates, and we have these affine coordinates. Just in passing, let's see. In this affine patch, this will be called the affine coordinates. In the 0, 0 chart. Okay. So in order to relate the two, we'll need to talk about the process of polynomials beforehand. Okay. So okay. Let's see. Okay. Homogeneization. So first of all, we'll talk about homogeneization. So what is this all about? I'm going to take a polynomial in n variables. Okay. So imagine that it's something that will cut a hypersurface here, and I want to make something out of it so that I can define a hypersurface here, but it is not homogeneous. And furthermore, it only has n variables. Well, the homogeneization will give me a polynomial to cut out the hypersurface on Pn. So how do we do that? Well, first of all, I need to know its total degree. Total degree. Now the total degree, remember, we consider all of its monomials and we take the monomial of highest degree. That will be the total degree of f. And we take f of h is equal to, we consider an extra variable here, x0, and we implement inside of f these quotients. Now, this won't be a polynomial unless we multiply again by x0 to a certain power. And the minimal power to which we need to multiply here will be x0. This is the homogeneization. We obtain a homogeneous, this is a homogeneous polynomial. Of degree d. So just an example, just a couple of examples to see a bit how this thing kind of works. Let's see. Yeah. Consider x1, x2 minus 1. Okay, so what would be its homogeneization? Well, the general way we do it is we look at all of its monomials. So this is the highest degree monomial, it's degree 2. And we look at the other monomials. So this is just one. Okay, there's just another one here. And this one is of degree 0. So we actually, so the homogenization, what it will do, it will add the powers of x0 to the monomials that are smaller than the biggest one. So this will be x1, x2 minus x0 squared. Okay? We need it, this is degree 0, this is degree 2, so we just need to raise to the power x0 2 in order to have this correspond here, like that. Okay, so this is an example. Let's consider just an extra one. So if I have x0 is x1 squared minus x cubed, x2 cubed. The total degree is 3 here, and the other monomial is degree 2, so we just need to add a power, 1 power of x0. Cubed, like this. So there's just an x0. Okay, so this is the homogenization, and of course there's an opposite effect. This one is even simpler. I take a polynomial here, so it could be homogeneous or not, it doesn't really matter here because we can always define g of I in variables x1, xn. Well, it just be I'll just take g and evaluate only the first variable at 1. Okay, so this should remind you of how these two things work. Okay. So now, equipped with this, we can actually define the relationship between the two topologies here. Okay. Okay. So let's make a proposition of it. So let's see which direction first. Okay. Okay. So let's consider a projective variety, well, a projective subset, even just. And let's say I want it intersected with its image AN here. So, like this, right? Well, if this will only be, if I want to consider it as an object of the affine set, this will only be A for affine, where this is just, let's see, G of A or G inside of G. Yeah. Okay. So there's also an opposite direction for this. So if I consider an ideal VA of I, but if I consider the affine set here inside of this inside AN, then I can actually consider it as a trace of a projective set. So this will be a projective set. Okay? And as you can imagine, this will be just the homogenization of all the elements inside the DLI. Okay. Okay. And in fact, V, so this image here is will be the projective closure of the A of I. So this will be really VA of I will be the closure for the Zariski topology. Okay. Let's see. So, okay, let's try and draw a little bit some diagrams to see a little bit how these things work out. Okay. We'll consider a very simple case, but this is just to see a little bit how things work out. So, example. Let's consider only a principal idea. We only have one equation, okay? So, which one? Okay. So this will be the equation of something resembling a hyperbole. Okay? So let's see, where should I draw it? I'll draw it here. Okay. So this will be a rectangular, well, no, like this. Right? So this will be x equal VA of f. Okay. Now the homogeneization, well, we add an extra variable. These two are degree 2. This is degree 0, so we just need to add here x0 squared. Okay. Like this. Okay. And, well, it is an exercise. The exercise I want to say about the following is that now this is a very interesting case. The homogenization of the ideal will be the ideal generated by the homogenization. If the ideal is generated by extra elements, this is false generally. If we take a generating set and you just take the ideal generated by homogenizations, you obtain too much points at the infinity. The other points you have, the extra points you obtain at the infinity are too many. And in fact, if you want to know how to compute the homogenization, you need to go to Grobner basis. If you have a Grobner basis here, a certain Grobner basis here, then indeed you can pass on to the homogenization of the generators of the Grobner basis. But this is a little bit too much. For the case of one, this is very easy, and it's basically just the hint is just that the homogenization of a product is the product of the homogenization. So this should be basically the answer. Okay, so we have that, and we want to know what are the extra points we obtain by looking at these the homogenization. Okay, so the points at infinity are the points of homogeneous coordinates. Well, x0 would be equal to 0. So it will be the points of these types of coordinates. Of course, x0, x and y should be both equal to 0. So 0 different or 0, 0. Okay. So inside of this, so if we insert these two in the equation, we obtain the equality like this. So either x is equal to negative to plus y, or x negative y. So the extra 2 points, there are only extra 2 points. 0. So since none of the two are 0, they are both non-zero, and we can rescale by dividing by x, so we will always obtain 1 here, and we either obtain for y the same thing or the opposite. So we obtain 2 extra points only. And in fact, these 2 extra points, you can actually kind of represent them as the asymptotes of this, of the parabola, of the hyperbola, sorry. So, let's see. Maybe I'll take red color. So I'll give them some colors. So the first point is 0, 1, 1, 1. Okay, so this will correspond to this here asymptote. So this point will be somewhere here, but you also find it on the other side. So this is kind of one of the interesting things, is that these 2 points will actually connect the 2 branches of the hyperbola at infinity. So this branch here will meet the other branch at infinity for this direction. So if we go at infinity here, it will come back through here, like that. And the other point, well, it's the other point that you can meet in this other direction, like that. There's also a 3D, a more, let's say, a 3D picture of this. So also draw this one. Okay. So this is actually, so if I consider just this equation here, this is actually the equation of a cone in 3D space. If I consider again the cone. I know that there's a kind of a joke here because there's a cone and the cone of the cone, which is kind of a misnomer. Okay, so the cone here should be represented like in blue, because this is going to give us the hyperbola. Or imagine we have something like this. Like this. So in 3D space, this is the basic image of our cone, like that. Okay. So this is x1, this will be x0, and this will be x2, like that. Okay, let's imagine this. And if we consider the affine piece, so this blue section here is only the affine piece corresponding to x1 equal to 1. So unfortunately, I'll have to like draw something a little bit strange. But imagine that there's a plane here. Let's see, like this, maybe. It's not really that great, but. And this will give me the section with the cone will give me the hyperbola. Like that. Okay. And the points at infinity are behind it. Well, are associated to something which finds itself behind it. This time going through 0. So this is x0. And the extra points that are going to be at infinity are going to be correspond to two lines. One going like this. So let's see. Yeah, it's kind of weird to draw it like this. But imagine that the cone will be cut. Actually, this cone should be something like that. Okay. So the cone will be cut this time through its axis, right? So you will have these two lines at the extremities. Right? My drawing this is a little bit fair. Imagine that, okay? And these two lines will correspond to 2 points in the projective space. My drawing is a little bit. This one here should represent everything you need to know about this quadratic. So it's a quadratic, of course. Okay. So this usually is more or less given in projective geometry course. For instance, when you try to learn about homographic transformations, or if you want to use, let's say, projective geometry to do something about affine Euclidean geometry in AN, sometimes it's a lot easier to do transformations and reason inside the projective space. But algebraic geometers do this as well. Okay, so let's just keep that one. Okay. So once we have done that, the other thing I wanted to talk about before we move on was about, again, trying to link projective varieties together. So remember, we have our objects, now we need our morphisms. So how do we proceed about morphisms? Well, the first idea was, as you remember, the strategy we used for affine sets was to define regular functions. And the morphism will basically be something that will transport regular function for regular function. We'll pull it back. Okay. So let's do basically the same thing, but we need to be a little bit careful because defining functions on the projective space is a little bit delicate. Okay, so let's consider projective subsets. Okay, so maybe basically anything. Consider a point P on Y and F. Yeah, let's a map. Okay, it associates to any point something inside. Well, sorry, no, that small big. It's basically. Okay, a map. So F will be a regular function. If, well, regular function at P, sorry. If there's an open subset inside of the topology of phi, it contains the point P, of course, such that, well, F of, let's see how I say this, F of A is equal to J, like a quotient of two things. Where J and H, okay, there are two homogeneous polynomials of same degree. This is the extra important thing here. Now, why is this essential to us here? Well, it is so that we can actually define the value here of the quotient. The idea is that, you know, that if we consider two homogeneous coordinates of A, they differ only by a scalar multiple, right? So if we consider the two, then the two images here will be equal because they will have the same degree. So just so that we can all be on the same page. So this is a parenthesis. So this will be g of x, but multiplied by a certain power of lambda. If I consider lambda a scalar multiple, and if they are the same degree, then we obtain the same power here. So we can simplify this extra bit here. So the same thing here. So g of A over h of A is well defined if we consider its homogeneous coordinates. This is the basic thing. Okay. Now let's see here. Where is this next? Okay, so this is one of the definitions, so the other one is a morphism. So if I consider a function between two projective varieties, so a function between two projective, or actually this you can even just consider quasi-projective varieties or subsets. And we will call it a morphism. It is a if for all, let's see how, yeah, regular function on y. So imagine that u is an open inside of y. If I pull it back by precomposing with f, so G composed with f, like this, is a regular function on x. So if I have a regular function on y, I can decompose it with f and obtain a regular function on x. Now this is a very general definition, but let's try and build a little bit our intuition about this, these things, these morphisms, with a couple of examples. Okay. And in fact, these examples will kind of deconstruct this, this definition of what a morphism should look like, more or less. So, okay, the most basic one, maybe some of you know, is a homography. Okay. So if I take a matrix, okay, let's consider an invertible matrix of size n plus 1, the coefficients in K. So this will define a actually an automorphism Pn to Pn, which looks like on the homogeneous coordinates, just basically looks, so if I just abbreviate the homogeneous coordinates just by one letter x, I can consider it as a column vector, so I can multiply it by a, and I obtain something which is also, so this is not zero vector, so this will not be a zero vector either. So this is how I obtain a very basic example of a morphism. So this kind of is very interesting because homographies are already a very interesting example in, let's say, classical projective geometry. Just like, well, I don't have the pictures anymore, but if you remember the picture of the cone and the hyperbola that we obtained by its section, just by a simple change of variables, the cone would be shifted inside the picture. And then you can, let's imagine that the cone, its axis was like this in one picture. Imagine that we can shift it like this all of a sudden. And so the section, the affine section we obtain, will go from a hyperbola to a circle. So this is kind of how homographies play a very interesting role already in classical projective geometry. Okay. Right. Sorry. Okay. I'll just erase this. Already? Okay, cool. Okay, so let's consider another example this will be projections. Projection from a point. Now, this is just to talk about homography, projections. Okay, so these are, you shouldn't confuse them with, you have your basic intuition and you need to find a morphism, something like that. Well, this is actually what we'll do, but the idea is the following. It needs a little bit of intuition to do it. Okay, so we set the point with homogeneous coordinates 1, 0, 0, all the way. And in fact, you can define a projection by outside of the point A to P of n in the following way. You consider x0, xn plus 1. Okay, maybe that was not a good idea. And you consider, so if it's different from the point A, the part which finds itself beyond x0 will not be equally 0. Otherwise, it should be equal to it. So you just take this chunk and you put it on the other side, like that. And this actually admits a very nice picture. So let's suppose that our point is here, right? Well, actually it should just be here. And in fact, if you remember the affine charts, this is actually the origin of the affine chart. x0 is equal to 1. Right? This is A. Right? And if I consider all the points where x0 is actually equal to 0, so this is x0 is equal to 0, this is actually the points at infinity of the affine chart. And as you can remember, you can identify it with P of n, right? So if I have a point here, let's say point P, of coordinates x0, the way I can find its projection is very nice. I draw a line between A and P. It will necessarily intersect the points at infinity. And this is going to be, well, I didn't actually give it a name here. I'll just call it P of A. And so this will be P of A of the point P. Pi. Sorry. Okay. So this is how I define this projection. Now, as you can imagine, this can't really be extended beyond, you can't actually define the point, the image of a point A, because depending on the direction you go, you obtain very different images, so it's not very well defined. However, if it is restricted to certain varieties, you can. So, it can be extended if restricted certain subvarieties or certain subsets, it doesn't matter. So again, let's talk about conic. Right? I'll go like this. So if I consider the conic, let's say 0 is 2 minus 6 1 like this, the image will be like, let's see, point A is here, and the conic one should actually represent itself something like something like an ellipse like that. And if we consider a point P on the conic, then again, well, we can just define the points, the image of these points like this, and what happens to the image of the point A? Well, here you only have to consider the tangent line going through A, and this is how you can define, well, tilde, because it's restricted to the okay. So this will be P of 1 because we are inside P of, this whole image is inside P of 2. And the points at infinity will be P1. And actually, well, you can actually look at the what is going on in the picture. This will actually be an isomorphism, actually. So P tilde is an isomorphism. So it will give us that our conic is isomorphic to P1. Now, let's see. Okay, yeah. So, I said that P1 is just P of A restricted to X, like that. And it will take a point So how could we actually define this extension? Well, if it's outside of the point A, then this will be defined just like projection. But we can also define it by projecting to the other side of these homogeneous coordinates, and it's well defined because x0, x1 is equal to x1, x2. And why is that? Well, that's because x0, x2 minus x1 squared is the determinant of, let's see, x0, x2, x1, like that. So that means that these two rows are always collinear on the conic. Let's see. Okay. So this shows us that this conic is isomorphic to P1. And through homographies and the classification of quadratic forms in 3 dimensions, you can actually show that every conic is every non-degenerate conic, so meaning that the quadratic form comes from is non-degenerate. Every non-degenerate conic will be isomorphic to P1. So through this image. Okay. So this kind of gives us a hint towards another example. So let's see. Okay. So we can actually consider a little bit of a more general example. So consider y is a projective. Okay, let's consider a projective variable. So that's irreducible, everything is nice. We will define its homogeneous coordinate ring. Okay, so this is the homogeneous coordinate ring. Okay, so kind of like the same object we did for the affine case. But the problem is that the objects inside of here are not easily interpreted as functions. So how do we improve it? Well, but we can kind of remedy it. Consider let's take m pieces of let's see across, which will start at 0. Homogeneous of same degree. Homogeneous same degree. This and define well, okay, no, not n, but rather y. Let's see, this is small. Okay. Pm, and the way we define this is I take a point inside the homogeneous coordinates here, and I just take the image of homogeneous coordinates on the other side with, well, with this. But there's a problem. There's a small problem. These functions f0 and fn can sometimes be all equal to 0. And this is not what, and this here are homogeneous coordinates are not well defined. So I need to actually get rid of the common zero locus of the fi. And this is exactly the way we did, and this is kind of the generalization of the projective projection. Well, the f0s were simply the coordinates x1 up to xn. So this is why we needed to get rid of the common zeros. Yeah. Okay. And okay, this is a kind of a general way to give us. Let's see where I'm. Okay. To give us morphisms. Well, morphisms defined globally. Sometimes it's difficult to give. Okay, and just to finish it off nicely, I'll use this construction for 2 extra examples, which are, well, historically important, but in general way they are very important as well. The Segre embedding and the last one will be the Veronese embedding. Okay, so what's the idea of the Segre embedding? The idea is to take the product of two projective of the two projective spaces, right? So, and we would like to see this this set as a projective variety, right? Because up until now, everything we saw was inside the biggest set we obtained was the projective n space. So we want to have a projective space inside of which this thing here lives. That would be very important because that would mean that we can have products of varieties will always be a variety itself. So how do we do this? Well, the names on the board. So the basic idea will be to, okay, let me just write this stuff. Okay, maybe you wonder why did I put this here? Well, how does this work? I take a point with homogeneous coordinates xy on the left hand side and xj on the path on the other side. So this is a couple of coordinates. And the thing I'll associate on the other side will be doubly indexed zi ij, well, this will only be just the product of xi and yj. So you think, well, this is kind of an easy object. And this is well defined because here you have one coordinate which will be non-zero, the same here, so their product will also be non-zero. So this will always be well defined. The end object here is binomial, so you think this is well defined, and it is. Let's see. Okay. And it's, let's say that I call this sigma. Sigma as in S of second. So the image of sigma will be a closed subset, it turns out. And the, well, let's just, okay, let's put it over here. Okay, so yeah, let's try and use some colors here. Yeah, okay. Yeah, like this. So if I take the product of two z variables here, so let's say ij and kl, if I write it down like xi and yj, well, I can actually intervert the I and k, because they're both x coordinates. So this is why on the other side, I'll obtain, let's see, z. So the right coordinates will be the same, but I will intervert I and j. So I and k, sorry. So k will be found here, and I will be found here. Okay. Of course, I, j, k, l are all good indexes. So you can actually prove this. This is a neat exercise to see if we to manipulate a little bit some coordinates. And in fact, let's see. Okay. And in fact, it is so let's call this X. It is an isomorphism between P n times P m and X. Now you may be asking me, well, what is a regular function on the product of this thing? Well, the answer would be something like, first, to define regular functions on the product, you just look at the affine charts on each of these, and so affine charts that will, let's see. So always do something like this, and this is isomorphic to an plus m. So you just need to look at functions from this to k and see what happens on the other side, so that everything holds up. This is just to say that if you want to have a product of two varieties, you can look inside of this bigger thing. And of course, the dimension here, well, it's just the number of different couples here, minus 1, because you always subtract 1 when you consider the projective space. Okay. And, okay, lastly, we will look at the Veronese embedding. Okay, so I'm going to finish this. Yeah, okay. So the Veronese embedding is a little bit more difficult to define, but okay. Let's consider two positive integers, n and d, and f0 up until f of n. So these will be polynomials in degree in in the values of x0, xn. You'll be the n plus d monomials of degree d. Let's see, is this correct one? Yeah, okay, but I'll need to consider this. Okay. Well, there's a simple counting problem. How many monomials of degree d are there in n plus 1 variables? Yeah, the answer is d along d choose n. So we consider these whole monomials, and we build, thanks to these monomials, we will build a morphism from P of n to P of great n. Okay, so they define a morphism. So P of n to P of n. So we have x0, xn, just like we did for the general way of constructing morphisms here. Now, the common zero of all these monomials will only be the origin in the n plus 1 space, because you always have the monomials x0 to the power d, x1 to the power d, x2, etc. So these all the only common zero will always just be the origin. So there's no real problem here to subtract. Okay. So one of the interesting things about this is that let's see. Okay, so let's call this new, or I guess this one. So one of the interesting things about this the morphism is that it passes from degree d hypersurfaces to linear hypersurface.
Hyperplanes.
Hyperplane, yeah. Sorry. Exactly. Linear hyperplane. So a hyperplane here will correspond to a hypersurface of degree d inside of here.
I think it's a good idea to denote this, to put index of this map, n comma d.
N comma d, yeah. Yeah, yes. Like that, yeah. True. So that we remember what's it. Okay. And okay, so this is hyperplane. The other way. Well, it's well, okay, so maybe I should have put this before, but it should be noted that the Veronese embedding induces isomorphism between well, P of n and its image, and you have, for instance, let's find an example of what this image should look like. Just to say that the image will be a little bit more complicated to define. So, for instance, the twisted cubic. So, the twisted cubic is a very simple example of a Veronese embedding. So, you start with P of 1, and you will embed it in P of 2. So this will be V of, so we start off with only one variable, right? And we consider degree 2 variables. So consider x and y, okay? And there are only 3 degree 2 homogeneous monomials. We have x squared, xy, and y squared, like this. Right? And its image is called the twisted cubic. And you can also prove that it is a set of points with homogeneous coordinates, so that it's, let's see, x1, x2, I don't remember, maybe
x1 squared is
no.
minus x0, x2.
Yeah, maybe I have, maybe I was wrong about this one. Let me just say, maybe there's a variable missing, but I don't really remember which one.
You want to find the equations of the image, or?
Yeah.
Well, x squared times y squared is equal to x.
Oh, no. Yeah, you're right. This is not the twisted cubic, I'm sorry. This is, I should have considered the cube here, so it's not, no. The image is actually the conic.
Yeah.
Sorry. The image is the, so, sorry. It's the conic V of x0, x2 is equal to the square of the middle one. Yeah, and this is actually the inverse of the projection we did last, the one I exhibited between the two. Okay. Now, if you want to have the twisted cubic, you need more variables. You need to actually go to the third part. Actually, this is twisted cubic. The method is more complicated. It is an image of V1 free. So it will be a curve inside of P3. So you have all the 4 cubic monomials. And this, yeah, okay, this makes more sense. And you can also see it as the set of homogeneous coordinates that the rank of a certain matrix is less or equal to 1. So this will be x0, x1, x1, x2. So you shift it on the other side. So let's see. Okay, so I shift it on the other side. X0, x3. So something like that. And so, in order to find the equations, you just take the 3 minus side of it. So these are the 3 equations of the twisted cube. Okay?
Particularly, this is not a complete intersection.
This is not a complete intersection. You have 3 equations for something which should have 2 equations. So it's a curve. You'd imagine you only have in space, so you need only 2 equations. It turns out that you can do some polynomial manipulations to obtain only 2 equations, set theoretically. But if you look at the ideal generated, the ideal of this variety, you cannot generate it with less than 3 equations. That's part of why this is kind of a weird counterexample. It's called a set theoretical complete intersection, but not a schematic set, a schematic complete intersection. More or less like that. Okay. So this gives us a couple of neat examples. And okay, so this more or less gives us the context in which, with the objects of which we will generally work. So let's see. Okay, I need to erase this a little bit. So generally, a variety will be any affine, quasi-affine. So remember, quasi-affine is just an open subset of an affine variety, projective, or quasi-projective. Variety. Now, there's a funny way to see about it, because if you consider Pn minus Vp of x0, so this is an open set, right? But we've seen that this is actually isomorphic to A of n, right? So this is a quasi-projective, but this is affine. So sometimes there's kind of an ambiguity going on. So the smallest one we could consider would be the quasi-affine, the biggest one would be projective, and sometimes a quasi-projective will be an affine or even a quasi-affine variety. Like that. Okay. Yeah. And in general, it will be covered by affine chunks, let's say. Right? Okay. So you will take a variety inside of P of n, and you consider all these open subsets. They, as we just said, it would be defined like that. Okay. Let's see. Yeah. Well. Okay. So maybe what I can do was start the next part of our study on singularities. So, yeah, maybe
Start
just just explain where we're going to be headed next Tuesday. So next Tuesday we'll start the study of singularities. So, just to kind of warm up a little bit this discussion, I'll just give you 3 examples that will be, well, very, let's say, very easy to understand, and will generally be very useful illustrations. So the first variety I want to give you is a parabola. Right? Very easy to understand. Let's see. So y minus x2. So in order to study singularities, we'll just study it locally. So we'll only be studying affine varieties for now. Okay. So a parabola, well, is a very easy thing to picture. It's like this. Okay. What about a node? So a node is slightly more complicated to draw, but very interesting. Okay. So this is a node. Because you can imagine that it's 2 strings tied up together there. And the final example will be what we call a cusp. So here we look something like this, and its basic equation is y squared minus x cubed. Like this. Okay. So the idea of studying singularity is a discrepancy between 2 ideas of trying to approximate our variety locally by linear subspaces. So in differential geometry, when we have something smooth, we can define its tangent space. So if I consider the origin here, the tangent, well, it's more or less easy to define. Like this. Right? But here there's a little problem going on. Because if we consider the origin here as well, there are 2 different ways we can say. First of all, when we define, if we would like to define the tangent space, we need to look at the gradient of the equation. But if we look at the gradient of the equation, we just evaluate at 0, the gradient would just be the 0 vector. So that would mean that the whole tangent space is the whole plane. This is a very good idea because we would like actually to say that there are 2 tangent directions here, this one and this one. So there's an ambiguity here. This will be the tangent space, and the 2 lines that are supposedly tangent directions is the tangent cone at the origin. Similarly here, we obtain the whole plane as a tangent space, which is a good idea, right? But only one direction counted double, which is even more weird, as the tangent cone here. So this is kind of what we're going to do next week. We'll talk about the tangent space, the tangent cone, and the origin, of course. And we'll try to find our first ways into more commutative algebra. Because when we study things very locally, we never unavoidably start going into commutative algebra. So we would study the link between what is a singular point, what is a smooth point, what is a regular point, and link it back to regular rings. Hopefully that will be already a lot of things to say. And yeah, I think I'll stop here.
Maybe it's a good idea for next time to draw more pictures of singularities.
Yeah.
Because we've been exposing people to just this good example. In fact, a good source of this is Karchor's book. In chapter 1, there is an exercise to match pictures with equations. And I think he has at least 6 or 7 pictures of more complicated singularities there that we can perhaps exhibit.
But they are very nice pictures, which is very interesting. Hudson became kind of, when he was retired, he became a painter. So he already had all this very interesting.
And then there is the pictures of Hauser.
Hauser surfaces.
Yeah.
There are many other singularities which are very weird, like this is called tactile. So you take a cusp and you kind of link it back on itself. Many weird things.
Of course, also algebraic equations. In general, not everything that you can draw can be described by equations. Algebraic equations.
That's true. Generally, when you try to define, when you try to draw curves, you can kind of do the real picture. But when you try to draw surfaces, you can more or less draw only 2 examples.